Ready to start the ring lecture? In order to successfully get through this lecture and get the most out of it, you need your model kits. Pause, go grab them if you don't have them. Keep those model kits with you for the next several lectures because this is the time of the class where it's heavy 3D spatial analysis and nothing's going to help more than that model kit. Okay, so remember we're trying to use the model kit to help us understand what's on the paper and be able to reproduce our own drawings on paper and create new ones. So we're going to start with the smallest ring, of course, cyclopropane. Essentially a triangle, right? You can see it drawn this way, that's the bond line format, but if you were to go ahead and get that model, so if you still have it built from last time, great. If not, go pause and build it again. You would have that model in the plane of the paper to represent this bond line format. Notice that if I do that, that means the carbons define the plane. Those 3 carbons define the plane. That means the H's are drawn as dashes and wedges because they'd be below the plane of the paper or above the plane of the paper. So let's draw those in because we know they're not always required, but for 3D spatial analysis, it's one of the first things you'll want to do if you're looking at something very closely in that region and you're trying to interpret it in 3 dimensions, then you should really draw in anything missing or implied. Okay, so that's one way to represent it that we are all well acquainted with now. But another way that you might not have seen too much till recently is if you wanted to let not the carbons define the plane. I mean, they are planar with each other, but if you were to let them be the ones coming out of the plane, so that's not the planar bit anymore, this is kind of coming out, which is hence the bolder sort of bonds here, indicating that we have the model on the paper with the 1 point coming out. So go ahead and do that. Look at your model. Look at only one vertex of the triangle. Let it come toward you. You'll notice that in the plane defined by those 3 carbons, 3 H's are above the plane, 3 H's are below the plane, right? So let's match those with colors. Let's let blue, in this case, just be above. So that would correspond to all the wedges that we had in the previous drawing. Let's let green be below. That would correspond to all the dashes we had in the previous drawing, right? Now it's asking you to sketch a Newman to show what's going on here as well. A Newman projection, we've been doing like crazy, but we did it with acyclic cases. Is it hard to do it with cyclic cases? No, because a Newman projection is simply any 2 carbons. So rings have more than 2 carbons. So you pick any 2 carbons and you look down that bond. So let's pick one. I'm going to pick, how about if I number these? 1, 2, 3. And then I let this be 1, 2, 3. It doesn't matter, right? It's because I'm not actually trying to name it. It doesn't matter which direction I go. I'm using this for a point of reference. So let's do a blue eye, just so color stands out. And we can look down. Which bond makes the most sense? You could look down 1 to 2. You could look down 3 to 1. You could look down 2 to 3. Okay, so let's go ahead and I'm just going to pick 1 to 3 because there's more space there. It does, like I said, the number, I picked green eyes, there we go. Okay, so now we're looking down that way. That means we're looking down from 1 to 3. So 2 is, in other words, not in there. All right, so I'm going to sketch a Newman. 1's in the front, 3's in the back. We'll worry about 2 in a minute. Now notice that we have 2 H's. Carbon 1 has 2 H's, and then it's connected to carbon 3 in the back, and then it has a bond to carbon 2. So let's just draw in that framework we see. Okay. Okay, so if you visualize kind of your head over here, you'd see these kind of come down, right, at your feet, and you have this coming up above you. So you're always looking for that Y shape. So here's that Y. So it's an upside down Y. Now, so that would be the blue H on my right, the green H on my left. They're both H's, so in this case you'd get away if you switched them, but they won't always be H's, so that's why it's important to be able to tell. So carbon 3 in the back, notice that 3 has a wedge. Both blue H's are on a wedge for carbon 3. And notice even more, and that's why this representation is useful, or the model. If you look down, so pick 2 carbons in your model to look down, you'll notice that the H's are lined up. Would you describe that as staggered or eclipsed? Eclipsed, right? So the H's are all eclipsed. So we need to draw an eclipsed conformation to get going. So let's fill it in with an eclipsed framework. Okay, so we notice that the H's are eclipsed. So wherever I found an H earlier, I have an H again. And notice that the blue H's are all eclipsed, right? And the green H's are all eclipsed with each other. So that therefore must be green, and this must be the blue. Okay, now what's up above my head? This is carbon 2. Carbon 2 is also connected to carbon 3. So it actually, I'm going to erase right here. I'm just going to write a CH2. And that's how you make the ring part, because it continues. It goes carbon 2 with the other bond to carbon 2 goes back behind here to carbon 3. Okay, so that's the Newman projection of a ring. It's the same as before. We decide whether it's staggered or eclipsed, get that conformation going. And then the trickiest part is probably just closing the ring back so that it connects to the other carbon, because these have to eventually loop back. Okay, so some things to analyze about cyclopropane. We know we have 4 bonds to each carbon, 4 single bonds, so therefore the hybridization must be sp3. So the ideal bond angle, as we know for sp3, is 109.5 degrees, right, for tetrahedral atoms. So tetrahedral. But the actual bond angle, I mean, look at your model. It's a triangle. So it's roughly 60 degrees. That is a big deviation, right, from the ideal bond angle. So there's a name for this, what we describe as something that disfavors or energetically. So this something that increases the energy of the compound. In other words, it's less stable. And we usually have a reason for that. Like, why is it less stable? Because the bond angle is not reflecting the ideal bond angle. It's strained. So this is called angle strain because the angle deviates from ideal, and it's also known as or ring, aka ring strain. Those are synonymous. So I'll put a little definition here just as you look back, but we essentially proved it here, right? Deviation from ideal bond angle in a ring system. So how do you know you have ring strain or angle strain? You look at the hybridization of the carbon in that ring. If that carbon wants to be 109.5, but it's forced to be way smaller or way bigger, you have angle or ring strain, right? So cyclopropane is not the most stable. Doesn't mean it doesn't exist. It's actually abundant. It's just not the most abundant for good reason, okay? So is there any way to relieve the strain? We know something about carbon-carbon single bonds, that they can rotate. And if they could rotate, can they change their bond angle? And the answer is yes for some rings, but not for this ring. You can try it in the model. The only reason you get any motion at all is because they use the bendable bonds, but it's too tight. You can't stop them from being eclipsed. And you can't make the bond angle look any bigger, right? So no, it's pretty much forced with that bad bond angle. We're going to see, as we increase the ring size, it gives it more room to rotate. We'll see ways for it to cleverly adopt a lower energy conformation. So we're going to work our way up there to the mother lode, which is the cyclohexane ring, which is what you see the most abundant in nature. Okay, so work your way up to cyclobutane. Okay, I'm not going to show the model for this one. You can feel free to build it, but it's analogous. I mean, you think of a square and what the angle would normally be in a square. This would be roughly 90 degrees, right? Still far from 109.5. And notice the other problem we also have is we have the eclipsing groups. So actually I forgot to also mention the fact that these are eclipsed up here. Let me label those. Eclipsing H's. That introduces a different strain. So it's not favorable to have them eclipsing. It's also not favorable for the bond angle. So there's also torsional strain. So torsional strain is when things are forced to be eclipsed. Ring strain is when the bond angle doesn't match. So there's two reasons that this is not particularly stable. Now notice that in cyclobutane, do we see eclipsing H's again? So I'm not using the model because I want to kind of train you to also be able to look at the paper without the model, because that's ultimately the goal. Use the model to fully understand what's on paper, and then slowly let go of the model until you get to really tricky, complex cases, which you will do all the way through the end of Organic 2. But it saves you some time to not take the model kit out every single problem, right? But in these few chapters, you probably will. Look at these H's all on the same plane, so they're eclipsing. So let's label that again. So that means we have, once again, torsional strain. So I'm answering this question, what types of strain are present? But that 90-degree bond angle right here means we have ring strain or angle strain. Now it turns out that it is possible to alleviate this strain, because if you build the model of cyclobutane, you will see you can actually bend some of them out of the plane. So what that means is it's no longer a planar square. It actually looks a little like this. If you build it on Spartan, you see it actually puckers. It's called the puckered conformation. Why does it do that? Well, first of all, it changes the bond angle. So it increases it slightly, and it takes away, look at how it's not in the plane. Therefore, the H's can no longer be perfectly eclipsing. To relieve torsional and angle strain. So that's the 4-membered ring. 5-membered ring, once again, does a similar thing. So notice that we have cyclopentane, but it doesn't stay planar, because if it stayed planar, all the H's would be eclipsing, and the bond angle would not be the ideal 109.5. So it does adopt this, it's called an envelope conformation. Notice it still has some eclipsing H's, so it's not perfect, but it can equilibrate, it bends back and forth between the two the several different, which one becomes the flap, in other words. So the envelope conformation, it looks like a little envelope that you're about to seal right here, right? So here's a flap you'd fold down. So this is called the envelope conformation. Okay, now we're going to get to the one we'll spend the most time on, but that kind of leads up to why this is the most stable one, cyclohexane. Build cyclohexane if you haven't done so already, okay? All right, so if you've built cyclohexane, do not just have the carbons. This is almost useless. It's good intention, because it's better than not building a model. But if you're going to put in any work, the work to go this far, just take the extra 2 minutes to complete it by adding all H's. So all H's need to be there. That's the reason that's why we draw the wedges in when we're analyzing in 3D. We only leave them out when we're ignoring them, but we're definitely not ignoring them right now. We're trying to understand what's happening in 3 dimensions, which means everything is being looked at. So put them all in, and as you build your model, let's imagine how we get this view that we've been drawing hexagons for some time. And yes, we will be drawing hexagons all semester. So some people draw the vertex down or the side down, doesn't really matter. But so that's the bond line format for that one. How do we view that with cyclohexane? Like if you just saw this, you wouldn't know that cyclohexane. It's because you have to look down the center of the ring. So position your eye so you're looking down the center of the ring. Now you can visualize where this comes from. However, in its ideal conformation, it's not flat. Well, this implies that it's flat, right? I mean, what would happen if it was flat? So you can make all of your carbons in the same plane. That would mean it's planar, in other words, flat. Look at the side view. When you look at a side with your eyes like this, you will see all the H's are eclipsing. We will also note that if it's flat, our bond angle still doesn't work out to 109.5. It'd be closer to 120. How do we know this? It's a little simple geometry. Actually, I'm going to use a different color because I don't want to, let's do some green. Do a little geometry to convert these to lots of triangles, because triangles are easy to analyze geometrically. And if we know one bond angle 60 for, angle in a triangle 60, we know the other one is as well. Then we know that the total bond angle for carbon would be 120 here. That is not a trigonal planar carbon. It doesn't want to be 120. It is not 109.5. Way more. So it has the opposite problem of the cyclopropane. Too big. So that would only be if flat. Second problem with it being flat is that, look at all H's eclipse. So there's torsional strain and there's ring strain. How can we relieve the strain? Well, we are just at the right ring size that we can make that zigzag structure that we find the nice staggered conformation for alkanes. Remember, that's why alkanes are not straight lines. They are zigzag to accommodate a tetrahedral carbon at each center. Six-membered rings just hit the right ring size to allow that to happen. You can have in other words, this is a zigzag ring. Okay? So in other words, we are going to bend the carbons in and out of the plane, above and below the original planar hexagon we saw earlier. So let's write that here. Bend out of, I'll put C's, out of plane. We say out of plane so much, I don't know if I've abbreviated this for you yet. OOP, O-O-P, out of plane. Okay, so I'll use that abbreviation a lot because we look at things in the 3 dimensions. So now take your flat, not stable cyclohexane and alternate carbons to be up, down, up, down, up, down. So when you look at it now, you see a true tetrahedron at each center, and you notice that they're no longer eclipsing. The H's aren't eclipsing. In fact, the top H on one carbon is completely staggered with the top H on the neighbor carbon. So you can actually visualize how they are not in the same, they're not aligned, they're exactly staggered. Okay, so this is called the chair conformation, where we are able to get all of them zigzag, but it doesn't do that right away. And it doesn't start off flat. It's essentially never flat. But we could also have equally likely made the other chair, which means knowing that single bonds rotate freely in solution, that this carbon's never going to stay where it is. It's going to go, if it's up, it's also equally likely to be down, which means its neighbors, in order to go back to a stable chair conformation, its neighbors have to alternate up. So what used to be up will be down, what used to be down will be up. And so there's actually 2 different chair conformations you can get, okay? So this is one of the possible chair conformations without all the H's drawn in. So notice it's a zigzag. It goes carbon down, up, down, up, down, up, back to down. Okay, so look at your model again and look at all of the ways that you can bend the carbons in and out of the plane, right? So you might just bend one carbon out of plane and let the rest be planar. Can you see which one that would match here? So we would get to this guy over here. This is actually called the half chair. I've alluded to the chair conformation before, and so that's clearly going to be the one that we see most of the time. And you'll see why. So it's because it's halfway to this one. So this is the chair. And why is it called a chair? It's not like your dining room chair. It's actually more like a lawn chair. So I'll draw real quick on the side, a little cartoon to maybe help you remember. But so if you have a person sitting in a lawn chair, let's make them happy because they're at the pool. And then you'd have the kind of headrest right here. And then where it's pointing down, you have your feet. That's the chair. It's there. So this, sometimes it's drawn a little more stretched out like this, where you can clearly see it. My computer program makes it a little more compact, but you can see this is the flap that folds down, kind of like an envelope. This is the flap that folds up. And you got kind of like a parallelogram here with two triangles. And why this is so great is for cyclohexane is because look what it does. Up, down, up, down, up, down. We have a zigzag conformation like we saw straight chain alkanes adopt. They're not linear. They go up, down, up, down, up, down to accommodate a tetrahedral center at each carbon. The chair lets you do that. So, but that requires alternating up and down carbons. So instead of just folding one up, you fold every other one up, every other one down. There's other ways you can fold it as well. So where you have maybe two down in a row, then up, two down in a row, then up. And then, or you could have, but also one up, two down, but theirs are more lined up. So this is called the boat, as you can see why. This is called the twist boat. So boat, twist, boat. And so the difference between the boat and the twist boat is simply these bonds here, whether they're aligned or not. So right here they're lined up, parallel, and here they're kind of, they're not perpendicular, kind of, but they're skew. Energy-wise, alternating is always the best in terms of most favorable. Okay, so when you read a question about ranking, read it very carefully because it's easy to reverse the trend. Rank the relative energy values from most stable, which means low energy. So most stable, better means lowest energy, to least stable, high energy. Okay, so from low, so since we're doing these less than symbols, I'm going to write low energy down here just to emphasize that, to high energy. Low energy means most stable. High energy means least stable. And so it's important to write that out just because it's easy to reverse trends when you have most and highest not matching. So most and least matches with highest and least, highest and least and lowest and most, and so it can get confusing. So write it out, spell it out, take your time. Okay, lowest energy means the most stable. We've concluded the chair is where it's at. And then what we're going to see is that we have a little bit of torsional strain introduced by having two groups in the same plane, right? That allows things to be eclipsed. So when you don't see an up and down, so this is by far the worst of all of them because it's almost all planar. Only one thing's out of plane. So I'm just going to go ahead. I think that's the most obvious. So let's put that at the bottom, half chair. But between the boat and the twist boat, which do you think would be lowest energy, more stable? Well, take a look at remember the difference between the boat and the twist boat is that these are lined up and these are out of alignment. So the fact that these are lined up means that not only will these eclipse, it will also eclipse with these guys. So that's definitely going to be less stable, more energy. So let's put the boat here and then twist boat here. So you might see this in your book or some other sources we use. The relative energies can be plotted. And in fact, these are all possible and needed to convert from one chair to another. Yes, there's more than one chair. So notice I showed you 4 conformations that we ranked, But let's put them in a graph to understand their relative energies. And notice I've drawn more than 4 here. I have 1, 2, 3, 4, 5, 6, 7. Well, let's label them to see what's going on. So this is a chair. And look at this chair. It's the mirror image of that chair. It's the other chair. Why are there 2 chairs? There are 2 chairs because, go ahead and make a chair in your model. Alternate up, down, up, down, up, down. When you do that, you will see that nice conformation that allows in and out of the plane to accommodate those 109.5 bond angles. But which carbon did you choose to put up? It was arbitrary, right? Could that carbon have equally likely been bent down? Yes. So because, now do the opposite. Bend that carbon down and make the others go up. When you do that, you did a chair flip. Okay? So that means that your chair can be this orientation or this orientation. There are 2 chairs you're going to want to know how to draw, identify, and build with your model. And we're going to take time on the chair flip. That's one of the most important things, but that's an equilibrium that's going on here. And as it progresses to the other chair, it undergoes these conformational changes. It can go through the half chair, twist boat, boat, other twist boat, other half chair. So this is the half chair where just one end is folded up. This is the half chair where the other end is folded up. This is the twist boat that's a mirror image of that twist boat. So let's just label them all again. So this is a half chair. This is the other half chair. This is a boat. Remember, that's actually a local maxima. And this is a twist boat, a local minima. And this is the other twist boat that you can arrive at. So let's connect them. Energetically, it'd be something like this. So notice the chair is the global, either chair is the global minimum. So I'll put global minima because there's more than one chair. And this is a local minima. This is a global maxima. And this is a local maxima. And in fact, these are in equilibrium. So in solution, they are adopting and going through these conformations, but ultimately spending most of their time settling into one chair or the other chair. And so when we do this, we have the all-important chair flip. So a lot's going on. The chair, saying a chair flipped is the simplest way to view it, but we want to recognize that a lot can happen from one chair flip to another. Okay. We understand why the chair allows for relief of angle strain. I mean, look at that staggered zigzag conformation that you get. You now have tetrahedral bond angles that are ideal, 109.5. However, have we relieved the torsional strain? And looking at your model, you should be able to see that, but we're also going to prove that with a Newman projection. And once you get to a cyclohexane ring size, we can do what's called a double Newman, because there are always in a chair 2 sets of parallel lines. So notice in a hexagon, in other words, we always have bonds that are parallel, right? So you can do a Newman projection down that bond, but that means there's also a Newman projection from that same perspective down this bond. Or you could say, I want to do this red bond, but that means there's another matching one there. Or you could pick this one and there's another matching one there. So because hexagons are made out of 3 sets of parallel lines that occur in pairs, right? Cyclohexane, of course, is the same way. So we can draw what's called a double Newman because we can always draw 2 at a time. Whenever we see one bond that we're looking down, there's a parallel set and we can connect them. So we're going to do a double Newman, and Then we'll practice drawing some chairs. Now, there's many ways we could put our eyes. Let's start this way. I think it's easiest to start here, but you might be asked to do it specifically a different way in some of your problems. So you want to be able to move around the ring. But because this is our first time, we'll do it from this angle because that's where you're kind of looking at the paper. So sometimes it's easier that way. Let's number our carbons. Okay. The numbering is arbitrary. I'm not about to name this compound. So I could have called it alpha, beta, gamma. I could call it 1, 2, 3, A, B, C. So I'm going to start here with carbon 1, 2, 3, 4, 5, 6. Once again, it doesn't matter whether I went clockwise, anti-clockwise. I'm just doing this so I can label it. All right, let's start with Newman projection for carbon 3, because that's what's in front. Carbon 4 is in the back. But my other eye is doing carbon 1 to 6. So you draw a second circle for carbon 1 with 6 in the back. Now take a look right here. We're going to connect them. Watch carefully. 3 and 1. How do we connect them? We connect them using carbon 2. Now if you envision yourself right there, would you say carbon 2 is above your head or down below your head with respect to this? Remember, we have to treat this chair as non-planar, and if we were to take a plane, or the original flat hexagon that you kind of derived it from, would you say this carbon pointed up out of the plane or down? So if you have to retrace this, kind of look at how my pointer has to go up in order to come to that vertex. That's an up carbon. So it's going to meet as at an up carbon. You're going to draw that same vertex. That's carbon 2. Once you draw that, you have the whole framework for your Newman to draw left. Set. It's all set. That kind of unlocks it. So has to be the Y shape, right? So if this is one arm of the Y, it has to look like that. You've got to draw those Y shapes. You can't draw it all squished. And what you'll notice right away, you might need your model to help you. If you look down, I'm going to make this match my model. If I look down and have a carbon 2 pointing up, right? Now look at my carbon 1, your carbon 1 right here. So match it with your model. Your carbon 1, the H here is staggered with, or anti to this H. And this H is staggered between these two H's. So it's staggered. They're not eclipsed anymore. See how there's an up H here and there's no up H here aligned with it. The up H is actually in a different part of the plane. So they're not planar with each other. So that means they're staggered, not eclipsed. So that's the other piece we need to know. Once we are in a chair, we can fill in our Newman by adding everything staggered. Okay, now how do we do that middle one? We're missing a carbon, right? 1, 2, 3, 4, 6. 4 and 6 connect via carbon 5. Watch how I trace 4, 5, 6. 4, 5, 6. 4, 5, 6. Notice that I'm going down with that vertex. So I'm going to go down now. Aha, now I have 1, 2, 3, 4, 5, 6. Okay. This is not a framework to memorize. It's a framework to work out because it will be different. I could have looked from a different perspective and had carbon 2 down and carbon 5 up. It just depended on how I numbered it and what perspective I took. So it's got to be worked out. Now we're lucky. We're starting off easy. Everything's an H. Fill in all the attached H's. I'm going to use black though for that. H, 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 H. This takes lots of practice, and once you get the hang of it, you'll get it for good. But why do we do this? Look at what it proves to us. It shows us why chair conformations are so stable. Groups are staggered in this conformation, right? We also have relieved ankle strain because we see that zigzag sort of alignment. And we've relieved torsional strain because we're staggered, we're not eclipsed. All right. Now, this is a drawing heavy chapter, so you'll need to practice chairs like crazy. Let's get some practice. So some tips for drawing your chairs. Chairs have 3 sets of parallel sides. All right, and then, so let's draw that first. I'm going to do a green. I always like to start with this way or this way. So the 2 sides. So let's draw both of them this way or this way. So we're going to draw both chairs. Now if you look at your model, if we look at it head on, we can't really draw everything. So it's just that we tilted it to the side a little bit. And when you tilt them to your right a little bit, then you're going, or to your left, you're going to see which way the front carbon needs to be. So if your front carbon is up, right, then which is the perspective I'm looking at, the front carbon's up, then if you're to the right, it's going to be, so let's see, if I have them pointing to the right, my front carbon's going to be up. So the blue's parallel, the red's parallel, the green's parallel. Now what I wanted you to do with your model kit is to pick it up, line it up with your face so that you can actually see these green bonds. Then note the front carbon that's pointing up, and notice how in order to twist it so you see it this way, it's got to be to the left of the back carbon. But you could have had the other chair where it's viewed this way, and that's the result of the chair flip, so we go like that, right? And when you do that, it's to the right. So let's draw in those blue lines again, and then the red. All right, so those are the possibilities. That takes practice. So that's part 1, getting those 3 sets of parallel lines. Okay, take a minute to note on your model that there's carbons pointing up and down, and try to translate to the chair. So I'm going to label these. Up carbon, right? Up carbon, down carbon. Up carbon, down carbon. Up carbon, down carbon. With respect to a plane that's there, right? Up, down, up, down, up, down. If the carbon's pointing up, look at our up carbons, there's a bond pointing straight up. So draw on that bond. Up, every other carbon is up. If the carbon is, so straight up, each carbon that points, I'm going to underline these, up, has a bond that points straight up. Each carbon that points down has a line that goes straight down. So look at your down carbons. Down, straight down line. Down, straight down. So every other carbon is down, and therefore it has a bond straight down. Notice this one in the back. I indicate that it's behind that red line by having a little break in it so they don't intersect. And now I'm going to fill the H's on it. These groups, the straight up and down lines, are the easiest to draw, which is why we're learning those first. Those are called the axial positions. So I'm going to circle them, and right next to them I'm going to write X for short, subscript X, just so we remember which ones are axial. Okay. Here's the harder one to draw properly, the other H. Look at these. So we've already drawn the axial H's. That takes away 6, 3 up, 3 down. The other 6 H's, they're on the periphery of the ring. That's why they're called equatorial. Like the equator, right? So this would be like the axis. This would be the equator. All right, so in order to draw those properly, you draw them parallel to the other side. So let's look at just one on your model. So grab one equatorial bond find what it's parallel to. It's not parallel to any bonds attached to that carbon that it's attached to. But if you look at the neighboring carbon, it's parallel to one of those bonds. So in other words, I'm about to draw in an equatorial position here, and it's not going to be parallel to green or red. It's going to be parallel to blue. So I'm going to match that color. So it's never parallel with the ones that meet that carbon that it's attached to. It's parallel to the other one. So if I'm about to draw it here, directly opposite this carbon is the blue. That's the one it's parallel to. So let's draw that in. Okay, let's draw on all those. Let's draw the other blue one. So the other blue one would be over here, parallel right there. Now let's draw in the green one. It would not be, notice how the blue doesn't touch the blue. So the green can't touch the green. So the red, and where the red and blue meet is where the green would be. Okay, and so it never points into the ring. It's along the equator, so it's going to go this way and this way. Now let's find the red ones. The red equatorial positions are parallel to the red. That means they're going to be drawn where the blue and the green meet, right here. So I do my best to be parallel, and it's not always perfect, but there is a lot of wrong ways to draw a chair, and very few, it's only really one right way, but the margin of error is a little generous because we're not all artists. However, it needs to be clearly an attempt to make it parallel, can't be in between. So let's draw in the H's. H, 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 and let's write EQ down there. I'm going to draw it in a square so that we can just easily see the difference. EQ, these are equatorial positions. Okay. All right, you need to practice this like crazy. Practice, 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 practice.
Always do it on my own, so I gotta get through it. And the only thing I know is to love what I'm doing. Never give up, never slow, till I finally prove it. Never listen to the no's, I just wanna keep moving. Keep my head up when I act, head up, that's a fact. Never looking back, I'ma keep myself on track. Keep my head up, staying strong, always moving on. Feel I don't belong, tell my thoughts to move along. Push myself to be the best, die with no regrets. Live with every breath, see my message start to spread. And I had so many dreams, then you hit your teens. Life ain't really what it seems, try to find out what it means. Always do it on my own, so I gotta get through it. And the only thing I know is to love what I'm doing. Never give up, never slow, till I finally prove it. Never listen to the no's, I just wanna keep moving. Yeah, I put out all this art, it's my only medicine. Yeah, everything I do, I'm just being genuine. Yeah, I'm sick of being screwed, feel my own adrenaline. Yeah, I do just what I do, and I hope you let me in, yeah.